Okay, so if you are having to watch this from home today, today is 5/21, and let's pull up the agenda really quick. Okay, so for today's topics, we are going to look at types of waves, wave drawing activity, and then we'll try to get into the wave speed equation. And so again, if you have to watch this from home, do your best to try to keep up with the content. Any access to homework, just see me for those. All right, so yesterday I had you guys working on the factors that affect the period and frequency of a mass in a spring. Now, these equations are not going to be things that you would have to put on your equation sheet for the exam or anything like that. There's an asterisk for it. But I want to show you that the period, the equation that you guys developed, or at least the relationships that you guys developed when you did your mass in a spring interactive, is that the period depends on the amount of mass that's oscillating and the spring constant of that spring. So M represents the mass. K is a factor for the spring constant. So the bigger the spring, the thicker the spring, the bigger that spring constant. And so what you should have seen is that as the mass increases, if the mass goes up, the period goes up. If the period goes up, that means the frequency must go down. And you should have seen that on your activity, that increasing the mass makes it take longer for it to go through its oscillations. Now, K is a spring constant. It's describing the stiffness, if you will, of that spring. If the spring constant goes up, then what we should see, since the spring constant is in the denominator there, the period should go down. If it's a stronger spring, it's going to oscillate more quickly. That means that the frequency would increase. Now again, these equations are not going to be things that you would have to use on an exam or on a quiz. But I would like to do a quick little demonstration for you on that. So I have two springs here. These are a parallel, or I'm sorry, what are called series arrangements of springs. So they're essentially the same kind of spring. They have the same spring constant. I'm going to ask Bree if you could help me with that one. Sure. Could you put that on the one closest to you? No, yeah. So yeah, you might not be able to reach that without that. Just be very careful. Right now, that is half a kilogram of mass. And so if you go ahead, you can get down to that. If you set that into vibration, you can see that it has to go ahead and pull it down, maybe about 10 centimeters. Let it go. And so that thing has a certain frequency of oscillation. You can see it sort of going up and down at a certain rate. Now, if I want to have something have half the period, so something that is going to, I'm going to have something that has twice the period. I want it to go through and take twice as long to complete a cycle. How much mass do I need to add on this other spring so that I can have, if this one's going down like this, I need to have the other one sort of go slowly through so that it completes one cycle when that one completes two. You turn and tell that person that you're sitting next to you how much mass I have to have on this to double the period. Take a moment and see if you can do that. I want to make the period be twice as great. Wow. Turn and tell that person that you're sitting next to you. You guys turn and talk? Good. I don't think the three young men over there did. You guys didn't turn and talk on that, did you?
Yeah.
You did? Yeah. Do you have an answer for me?
I would have said that you would check. No.
Yeah, we were saying. All right, now look at. I want to take a moment and make sure that you understand. You are choosing open seats. That's great, but you have to still respond to these things appropriately. Otherwise, we have to go to random seating. I don't want to do that. So just if I say, hey, turn and talk to that person, and you're choosing to sit next to these people, still have that conversation. Otherwise, we're wasting our time here. and I don't want to waste your time, and you don't want to waste my time. Okay, so let's try that again. Turn and talk, tell that person that you're sitting next to what you would have to do for the mass on that other spring to double the period. Let's try that. Realistically, can you guys talk? You guys are doing your job. I appreciate that. You guys talk through that. Okay, good. Make sure you do this. So I want to make the period be twice as great. If that took 1 second to go through its oscillation, so its period was 1 second. That took 1 second to do it. How much mass do I have to put on that one to make it take 2 seconds? You guys come up with something else? How much? Twice as much. Okay, thank you. I appreciate that. I make the mass twice as great. I would only increase the period by about 1.4 times, and that's because there's a square root there. So if I make the mass twice as great, and then I take the square root of 2, the square root of 2 is not twice. It's not 2. It's only about 1.4. So let's try that again. I can't just put 1 kilogram of mass in there. How much do I have to put to double the period? You guys talk through that? What did you guys come up with? Same thing, all right. So clearly if I double the mass, I would not double the periods because there's a square root in there. You guys come up with that? So if I put 4 times the mass, the square root of 4 is 2, and so that would double that period. Okay. So thankfully, I actually have 2 kilograms of mass here. Bree, you want to do this one for me? Sure. Now for this one, the idea is that, so you're going to connect these here. And so now you're going to take that one and attach that one there. Now it's a lot heavier. How much heavier? 4 times as heavy. So there's going to be 4 times as much mass that has to oscillate with this spring. And so when you allow that to go down, it's going to sink a lot further. So we have to stretch that spring a lot greater for that thing to be able to reach a state of equilibrium. Now, if you set that one into vibration, you can see it's still going, right? So there's very little damping on that. Go ahead and pull that down again about maybe 10 centimeters. And let it go. You can see that it's oscillating with a certain frequency, a certain period. For this one, what we want to do is we want to pull this thing down another 10 centimeters. And what I'd like to do is try to release it right at the time that this thing is at its bottom motion, right? So that you're going to try to have these things start at the same time, okay? So watch how many times this thing goes through its motion while that one goes through its motion. You should see that that is twice as frequent. That it takes twice as long for this thing to go through its oscillation than that one. So if this one's got a certain frequency, this one has half that frequency. If this one has a certain period, that one has twice that period. Okay? So that's what that equation is for. Now, yesterday I had you guys estimate the length of that pendulum. I'm going to show you guys the equation for the pendulum period, and I'm going to have you guys try to calculate the length of that. You should see that the equation looks very similar. It's a very similar kind of equation. Instead of M and K, it has L and G. G is, again, that acceleration due to gravity. Do you have a question? Okay, let's refocus on this. So what we don't want is distractions. Okay. Now, same idea. If you increase the length, then that's going to cause the period to increase. But it doesn't increase linearly. It increases related to that square root idea. I'd have to have 4 times the length for me to double that period. If I increase the length, the period will increase, the frequency will decrease. Now, we can't change G. without going to a different planet or a different moon or something like that. But if I make G bigger, so I take this pendulum to Jupiter, since G is in the denominator, that's going to make the period smaller. That means it will oscillate more quickly. And if the period becomes smaller, that means the frequency will increase. So again, if I were to take this thing to some planet where G is a bigger value, then it would have that effect. Okay, I'm going to have you guys try, in the space that you have here, see if you can calculate the length based on the period that we measured yesterday. And I erased it because my second hour had slightly different numbers. What was the period that we got for the pendulum yesterday? We wrote it somewhere, I think, on here, maybe around here. What was that period?
It was 6.7 seconds.
Okay, so 6.7 seconds. I'm going to have you guys see if you can go through and calculate the length of that pendulum using a period of 6.7 seconds. This is an enrichment thing. I would like to calculate L, knowing that G, what's the acceleration due to gravity down there in the Foucault pendulum area? What is the value of G down there? It's the same value that we have here in our classroom. It's our 9.8 meters per second squared. That's that value of G that we've been using since the beginning of this class. Go ahead and see if you can calculate the value of L based on the things that we were able to measure and things that we know. Okay, take a few minutes, see if you can go through and do it. It's a math-related concept. See if you're able to calculate. Once you have that value, I'm going to ask that you just raise your hand. I'd like to walk around and see that. Once you have that value, just raise your hand. I'd like to see it. If you're not able to do it, I'll show you the solution here in a moment, but I want to see where you are with that math-based skill. Once you have that value, just raise your hand. Okay. Yeah, so that's okay. I just want to see. Make sure you have some units on it too, right? So there are units associated with that. That's okay if you didn't get it. I'll show you the solution, but it would be helpful. I'd like to see where you guys are with it. And that's pretty accurate. So a lot of people overestimate the length. They're like, oh, it's 20 meters. Oh, that's actually, that's like right up. Are you really good? That's okay. I just want to see. Again, you're not going to be tested on this, but the challenge with a physics class is that we try to use as little math as possible, but in the real world, we need to be able to have you use some mathematics, some computational thinking, some computational skill. So I'd like to see if you're able to get that. There you go. For some units on. Pretty close. I think you could differ a little bit on there. I'm not sure. Did you use 6.7 seconds? Did you use 6.7 as well? Did you use 9.8? No, 10? Okay. You use slightly different numbers. So I'm not sure who's correct. They're close, but they're not exactly the same. So, were you able to get? Okay. It's not right, but that's okay. That's all right. I want you to try it. Were you guys able to get? Okay, I'm gonna again, folks. You're not going to be asked to do this on a quiz or a test, but that doesn't mean that it's not a valuable thing to try. So let's go ahead. If I'm going to solve this for L, first thing I'm going to do is I'm going to square both sides. So I'm going to take T, I'm going to square it. That's to get rid of the radical sign. So when I square the right-hand side, I get 4 pi squared. And then when I square the square root of L over G, what I get is just L over G. So my first step here is I'm just going to square both sides. Now I'm looking for L. So I'm going to multiply both sides by G and divide both sides by 4 pi squared. So that becomes G times T squared is equal to 4 pi squared times L. Then I'm going to divide both sides by 4 pi squared. So L can be calculated as G times T squared divided by 4 pi squared. Now, I know a lot of people like to do this with numbers as opposed to letters. But the nice thing about this solution is that any period that I have, I measure the period of a pendulum, that's the T value. I can go ahead and just plug that value of T into that equation and calculate the length based on any value, as opposed to having to go through and do that math every time. So I take 9.8, multiply that by the period squared. Now, the units should reduce to that length being in meters, and you can see that that's the case. Meters per second squared multiplied by a second squared value gives me meters there. So 9.8 multiplied by 6.7 squared. And then a lot of people will make this mistake when they go through to do the calculations. When I do the 9.8 times 6.7 squared, that's what I get is 439.9. Then I have to divide by 4, and I have to divide by pi squared. So a lot of times, if you don't use parentheses, you have to hit the divided by sign twice. And so then I'm going to square that. And so that's how I'd get that answer. So G T squared divided by 4 pi squared. When I do that, I get about 11.1 meters. And I think that's what you had, correct? Now, did you do yours using letters, or did you do yours with numbers? Yeah, most people would do that. The value, again, of doing the work in letter form, like I showed you here, is that now I can take any period that I measure, and I don't have to redo the math. I already have the equation written in terms of L. That's the value of this. Okay, you still get it right? But it's a nice, convenient way to do it. The math teachers, when we get together with all the other teachers and we do our early release stuff, I talk to the math teacher, and I'm like, this is a skill that kids need to have, is they need to know how to work with letters in equations, not just numbers. Because oftentimes in our chemistry classes and our physics classes, we have all these equations that represent relationships, and we want to work with those in letter form so we can move things around. It's a skill that the math teachers don't necessarily agree that that's an important thing, but I think it's super important for sciences because we often let these things represent real things, not just solving for X. In this case, we're solving for L, which is an important part for that relationship. Okay. So again, you should get 11.1 meters, and most people estimated yesterday that it was 20 meters or 15 or 17 or whatever. It's only about 11. Now, another way you could have done that is you might remember the egg drop was about 6 meters, and that ceiling out there is about twice as high as the other. Okay, so just a little estimate there. None of that's going to be on quiz or exam. It's just something that I think would be interesting or helpful for you to understand. All right, guys, some other things that we got to look at today, and we're just going to look at these different wave classifications. So it's based on the wave form is based on how the particles move. There are two types of waves that I want you guys to be able to identify here. One is called a transverse wave. Transverse represents a certain kind of waveform and associated related to which way the wave is moving. And then the other one represents a longitudinal wave. So transverse versus longitudinal. How the particles move in relation to the wave, the way that the wave travels. If I were to take a transverse wave is where my hand is moving perpendicularly to the way the wave velocity is moving. So you would see that my hand is moving back and forth like this at a right angle to the way the wave is traveling. So we would say that the motion of the particles is perpendicular in relation to the motion of the wave. So the wave is moving to the right, the particles are moving up and down. Now, a longitudinal wave, harder to demonstrate. We see that the particles are moving longitudinally in relation to the way that the wave is traveling. We would say that it is a parallel motion for the particles in relation to the way that the wave moves. So the wave is moving to the right, and the particles are moving right and left. Now there's a little visual here. Hopefully this one will work. Okay, so again, just a visual for you. Okay, now we can also have the type of wave. Now there are mechanical waves. Mechanical waves are, they require a restoring force, and they require a medium, if you will. So the medium is the substance that provides that restoring force. So there's a lot of examples of mechanical waves. Sound, when you guys made your speaker cups or paper speakers the other day, sound is a mechanical wave. It needs the air around us to be able to transmit. If we were trying to run those speakers in a vacuum of space, there wouldn't be any sound being transmitted. Water waves, earthquakes, ropes, anything like that are all mechanical. There's a medium that's required. Now, electromagnetic waves, things like light, do not require a medium. They can travel through, like our atmosphere, which is composed of oxygen and nitrogen and so forth, but they don't require it. So they can travel through the vacuum of space without any restoring force. As a matter of fact, the E&M mutual induction, the fact that electricity can create magnetism and magnetism can create electricity, that's what provides that restoring force. And so they're able to travel through the vacuum of space. Now, the one thing that's missing over here, radio, microwaves, infrared, ultraviolet, X-rays, gamma rays, those are part of the EM spectrum. The one that's missing, of course, is the visible range. And so Roy G. Biv falls into that area. And so electromagnetic waves, again, do not require a medium. Okay, it's 8:21. Not sure where we are with time yet. Give me a moment. I think that's probably a good stopping point. Okay, so folks, I'm going to stop the lesson here again.